Because we are working with non-Newtonian fluids, we have to characterize the rheology of the fluids, and for that we use a rotational rheometer for all kinds of shear measurements. So this is programmable. You can do several kinds of tests. And to assess the extensional behavior and measure also the relaxation time, we use a so-called capillary breakup extensional rheometer. It's essentially two plates. You put a sample in between. You suddenly move the plates, and then you follow the evolution of the diameter of a filament, which within a certain bounds of operation, this capillary thinning, well, this thinning is driven by capillarity and elasticity. And so the slope in a semi-log profile, in a semi-log plot, the slope varies as -1/3 lambda, and you take the relaxation time of the longest, of the largest molecules, which are the longest relaxation times. Computations, we use our own code. It's a finite volume code. We have been developing this one since about late 1990s. Uses collocated grids as a vast series of constant equations implemented. The main evolutions that we made were a specific high resolution scheme for computing the advective terms called the Kubishta, and more recently, the log conformation formulation of the stress, of the polymer stress, which was developed by Fatal and Kupferman, and which we implemented in a finite volume code, allowing computations at very high Weissenberg or Deborah numbers. I don't have time to go into detail, so let's talk about some results. And I will start with the flow in a cross-slot. The flow in a cross-slot is characterized by these two inlets with the same flow rate and two outlets. This is a visualization by Paolo Arrasia in Pennsylvania. And at very low Reynolds numbers, the Newtonian flow is symmetric. As you increase the Reynolds number, it remains symmetric. But if you add polymers and do the same experiment with a Boga fluid, so Boga fluid is a constant viscosity elastic fluid, suddenly there is a transition from steady symmetric to a steady asymmetric flow. So instead of having a division of 50% flow rate going to the upper and lower arms, it's a different ratio. Subsequently, Poole, Alves, and Oliveira computed using, dropping out the advective term of the momentum equation, so Reynolds zero computation, and using a Maxwell model. So they showed that for Newtonian fluid, the fluid was really symmetric, and then for a Maxwell model, there was, they could observe the same instability, the same transition from steady symmetric to steady asymmetric flow. By the way, this flow is used in many places to study the behavior of macromolecules, because there is a stagnation point in the middle. So in the center line, you only have extensional flow, no shear. Shear, of course, exists because of the walls, but along the center lines, you have pure extensional flow. Subsequently, we did a lot of work on numerically trying to identify the various phases using the UCM. So we have here a zero Reynolds number. You see the transition from steady symmetric to steady asymmetric flow. But then if you keep increasing the Deborah number, you see a second transition from steady asymmetric to unsteady flow. Okay? If you increase inertia, you eliminate this intermediate regime, and there is then transition from steady symmetric to unsteady flow. Okay? We have a bifurcation diagram using this quantity, the difference of flow rate that goes into one and the other arm, divided by the total flow rate. And this investigates the effect of adding a solvent to the pure Maxwell model. As you increase the solvent, there is stabilization because the bifurcation happens at higher Deborah numbers. And then above a certain amount of solvent, you actually don't go anymore from the steady symmetry to steady asymmetry, but you go directly from steady symmetric to unsteady flow. Okay, so you change. It's a bit like the effect of inertia. Okay. In their paper in the PRL, they computed. So actually, could this instability be due to the corners, having sharp corners in the cross-slot? Poole, Alves, and Oliveira showed that you found the same instability if you rounded the corners. And like in here, if you have a cross-slot with rounded corners, the flow becomes unstable. Of course, there will be a different transitional Deborah number, but the instability is there. What this shows are velocity profiles taking along the center line and also at 45 degrees for Newtonian, for Deborah number below the critical value, and then imposing flow symmetry at a Deborah number above the critical value. And they found, of course, that for that condition, the velocity profiles show a change in concavity. It's a bit like centrifugal instability in a Taylor-Quet flow. But this is also a linear instability. It's not so easy to compute the Pactel-McKinley criterion because it's never easy to find out what is the radius of curvature of the streamlines. But I will give you in a moment another example where it's very easy. We combine solvent and inertia effects to investigate, of course, these maps, these phase diagrams. So this has been extensively investigated numerically. Here, the computations I've just shown you were 2D computations, but we are now doing experiments in a special build cell. Of course, in microfluidics, the flow will be 3D. And we show here for the Maxwell model at Reynolds 0 the effect of the aspect ratio. So you can see that if you make it very thin, the middle regime of steady asymmetric flow disappears. And also, if you make the Reynolds number large, as we have seen, large meaning above 2, 3, it also disappears. That's why very often people don't see this region of steady asymmetric flow. The window, its window of existence is fairly small. Now, the flow in a cross-slot, the previous results were for pressure-driven flow, and now I will show you very briefly what happens if we have electroosmosis. So instead of the flow being driven by a pressure difference, it's by electroosmosis. What is this? If you have a channel made of dielectric material and you put an electrolyte inside, there's a spontaneous charge separation. So the walls will acquire a charge, and next to the wall on the liquid side, there will be counter ions. Away from the wall, the liquid is electrically neutral. So now if you put a potential difference between the inlet and outlet, this will impose a Coulombic force on the counter ions near the walls, and that fluid will drag the fluid inside the channel. And as a consequence of that, you have a velocity profile, which is essentially a plug velocity. The velocity here is called the Helmholtz-Shmolushkovsky velocity, and then you have a very thin layer of fluid with a very high shear rate. Okay, so if we drive with electroosmosis, the flow in a cross-slot, what we found is, we call it now electroelastic instability. So the flow is steady symmetric as the Deborah number is increased, and then it suddenly becomes unsteady. So you don't see the asymmetric steady flow, but the flow becomes unsteady. In this flow, because you essentially have a plug flow, it will be easy to see the validity of the Pactel-McKinley criterion. This is just a phase diagram, so we plot here the Deborah number defined on the basis of the thickness of this layer near the wall. It's called the electric double layer thickness, and the velocity of the plug, okay? And if the kappa is actually the normalized value of the inverse of the thickness of the electric double layer. So the thinner this thickness, so the wider the region of plug flow, the larger the value of kappa. So you can see that the transition Deborah number is constant, and it's very easy to compute or to estimate the value of M critical because the radius of curvature is essentially the radius of curvature of the streamline is essentially the thickness of the electric double layer, and then it's for fully developed and for a plug flow, for a Quet flow or for a constant shear rate flow, it's easy to compute the shear stress and the normal stress for a UCM fluid. The shear rate is essentially the velocity in the plug divided by the thickness of the electric double layer, and you compute you arrive at a linear relation between kappa Deborah as a function of kappa. And then if we look at the values of the Deborah numbers for different kappas where we found the instability to occur, we can fit really a straight line. It fits well, so giving you an M critical value of 7. So in the case of the cross-slot flow driven by electroosmosis, it is easy to compute the radius of curvature of the streamlines. Of course, for pressure-driven flow, it's a bit more complicated. The flow focusing device is a cross-slot, but now instead of having 2 outlets, you just have 3 inlets. And in addition to the Reynolds and Weissenberg number, you have the velocity ratio. So these two inlets are identical, and you have here a third inlet. So I will now only go through the other flows to show you some pictures and films. For Newtonian fluid in the flow focusing device, the flow is always symmetric. It develops, there is a recirculation, well, a separating flow. In this case, it's a 3D structure because these are experimental results, and the red lines are streamlines or strict lines from the computations. So the comparison between Newtonian and non-Newtonian are quite good. There's at a high velocity ratio, so when the flow here through the bottom inlet is small, it develops a 3D structure over there. What is relevant is that when you put a non-Newtonian, these are pictures of the Newtonian 3D effects, but the flow is always symmetric. This is the important thing, and steady. Unless, as I said, you go to very high Reynolds numbers. Now, if you put a viscoelastic fluid, you see again an instability. The flow now, the cross-rod is twisted by 90 degrees, so the center inlet is this one. At low Weissenberg numbers, the flow is symmetric, but then it becomes asymmetric. And the pattern is the same as we found in the cross-slot, steady symmetric to steady asymmetric, and as you keep increasing the Weissenberg number, then it becomes unstable. Okay? The computations that we did are 2D, much cheaper. They also show the same features, steady symmetric, steady asymmetric, and asymmetric, but we didn't attempt to match the computations with the experiments, okay? Right, these are the phase diagrams for the experiments. You see the region of asymmetric steady flow. And for computations, of course, the computation is 2D, Maxwell model, no attempt to match the rheology of the UCM model with the rheology of the solution of polyacrylamide with salt, a Boga fluid, but qualitatively you see the same regions and the same regimes. The hyperbolic contraction was the first attempt, actually is the first work that we did in microfluidics. The idea is to have an hyperbolic contraction here, is to have a region of constant strain rate. Then we could measure the pressure drop, and that would be a measure of the extensional viscosity. We found that this did not work very well. We are still doing work with it, but for other purposes. Anyway, I want just to show you that if you know the rheology well, in this case Newtonian, then the measurements and the computations, they all match. The measurements are the symbols and the lines belong to the computations. What is more interesting is what happens when you put a non-Newtonian fluid, like again an elastic fluid with constant viscosity. The flow is from left to right, so the flow is symmetric. Then it becomes, there are recirculation zones upstream of the contraction, okay, which then become unstable. But the films are more interesting to see that. So low flow rates, low Weissenberg numbers, everything remains steady. This is a solution of 0.3% of polyethylene oxide in water. Then if you increase the maximum flow rate to 7 milliliters per hour, you can see that the flow becomes really unstable. The Reynolds numbers are small, things of the order of 1 or less than 1. Okay, so it's really an elastic effect. Out of this hyperbolic contraction, we can make what is called the hyperbolic rectifier, which is a series of hyperbolic contractions. The idea is, of course, the flow in the forward direction is different from the flow in the backward direction. Essentially, the flow in the forward direction will have instabilities at different